Hello everyone. Our next talk will be analyzing Android malware by Vanja. Please welcome.
Thank you. Welcome to this early morning session, really. Analyzing Android malware from triage to reverse engineering. Okay, it's a little bit ambitious, but let's see what we'll try to cover in this. It's a very brief period of time, of about 45 minutes, where I'll try to kind of cover some of the basic bits of how you do some Android and malware analysis, and in general, reversing on Android applications. And then kind of dig a little bit deeper, that's a little bit more advanced around some dynamic binary instrumentation with Frida. And I'll give you some pointers at the end where you can actually try to find more information. So my story, every presentation will have a story. My story is that 10 years ago, I was working almost exclusively on analyzing Android malware, and then I didn't do it, and I ran away like crazy from it. And then I thought, okay, so after 10 years, perhaps now it would be a good time for a refresher. So therefore, this presentation, which was helped by my colleague, Victor, who is very much more enthusiastic about Android these days than I am. So he developed a course that I kind of compressed a bit, and I add some bits, so bear with me, and hopefully we'll all have a bit of fun and we'll learn a bit. So we need to start with a very high-level overview of what Android is. It's an operating system on top of Linux kernel, and it has, now we see the view of its architecture from very high level. At the top, we see Android, we see system application and user applications. Then we use Java API to program it, and you can also use Kotlin, which is maybe even more popular these days. But generally, it's kind of looks like a Java virtual machine in the middle, with many different set of classes and objects that allows you to create user interface, communicate with the system, with the file system, with networking and so on. Everything that's required to expose normal functionality of the operating system. Just below there, still in user mode, we have native C++ libraries and runtime. Like at the time when I was doing the analysis, the virtual machine was called Dalvik virtual machine. Now it's called Android Runtime, and in fact when we installed Android apps on phones, they get part of it or partially or fully compiled ahead of time, and they get converted into different bytecode that's now run by Android Runtime. But for the purpose of like reversing and malware analysis, we really need to know two things. One, for basic analysis, we need to understand some Java and how to kind of reverse those applications, but we also need to know some of the like binary assembler, and most of the time it will be ARM, but Android is a multi-platform, or it can run also on Intel architecture, on some other ones, almost in the same way as Linux. So below that is the kernel, the standard Linux kernel, and there's a hardware abstraction layer, which on the lower side communicates with the kernel, but on the top side it communicates with the drivers that are provided by any of the smartphone kind of manufacturer for their own device set or chipsets and so on. In terms of the security, it's kind of initially, at least in theory, very well thought out or thought through. Every app is running inside its own sandbox. That sandbox has its own user ID and application ID, and in theory, only the same user ID and application ID should have access to the private data of that application. It's a security-enhanced Linux underneath with the default deny policy, and every time we install some application, and I'm sure you're aware that you need to approve some permissions that are requested by applications, and sometimes some permissions are requested when they are actually being used. And there are a few functionalities which are used and abused. It used to be that this device admin functionality for mobile device management. Now that's slightly deprecated, and device owner, I think, functionality is used. But overall, with Android security, there is a bit of a mess because there are so many different vendors. There are so many different phones which are new and old and not supported and supported. So overall, as an ecosystem for applications, we have to also remember that Android is not just installing apps from Google Play, but from the third parties. You can sideload applications, and overall, it's not so great. And I'm not really surprised that I kind of run away from trying to analyze it. Primarily because the main class of application, if you work in anti-malware industry, you will work on Android, will be so-called potentially unwanted applications, not real malware. And they are like built on top of hundreds of different advertising framework, and to analyze all that, it really is not a pretty sight. But there's also a silver lining to this. Apps are relatively easy to analyze. Although there are some obfuscation and packing techniques that are used, there is plenty of good free research tools that are developed over time, and there is at least one powerful dynamic binary instrumentation framework which we will cover. When you look underneath to the actual file system, APK files are nothing more than zip files. You can just use any unarchiver to unarchive it, but they have a specific structure that every application needs to follow. And there are some important bits in that file. Probably the first bit or first part of the APK structure we will look at will be the manifest file. The manifest file is an encoded XML file which declares all the permissions that are required by an application. So if the application needs to send or receive SMS messages, make call, receive calls, the permissions are grouped into several groups. There are like permissions which no questions are asked to the user. Then there are so-called dangerous permissions, such as receiving SMS messages or making calls or redirecting calls. And then you have signature or like platform-based where the actual publisher of the permission needs to be the same. The signature for the application that publishes the permission should be the same as the signature of the application that needs that permission. So that's the highest level of security. Then we have classes.dex. Dex stands for Dalvik executable. It's a town in Iceland, and that's called Dalvik, and the Dalvik virtual machine is running Dalvik executable code. And so this is the main thing we will try to target when we try to decompile or look at the static analysis of the code. And there are some other interesting bits, like if the application is using accessibility services, and accessibility services is probably the most misused part of the Android. And they're specifically made when some people are disabled or have some disability, or even like a temporary disability, and allows the apps that use those services to make actions for that particular user, so the applications can read text of other applications, that they can detect when other applications are loaded, and so on. There'll be some configuration files to filter which messages are filtered or used from the accessibility. And this accessibility is used by phishing malware, by ransomware, by various stealers, and so on. Like almost every proper malware will try to get to the accessibility bit. So here is there's a tool called APK tool. That allows us to dump the manifest file, and here you can see like various permissions. These permissions are taken from the Metasploit stager, which is also like can run on Android, when I was doing this preparation for the course, I kind of tried to find one application that doesn't have any native components. Like one of the things that I failed to mention in the previous slide, which are very relevant, is that if you see these files in assets and underneath ARM64, ARM application binary interface, there'll be some .so files. And they stand for share objects, and they will contain native code. So this is what I said when you need both knowledge of, let's say, Java to read and understand, and also the knowledge of the native code. But for the purpose of this really brief presentation, we'll mostly look at the Java code. So the next thing we need to be aware are some basic parts of the application. Every application will have their own basic structures or basic objects. The first one will be the activity. Activity is something that is focused on one thing that the user do, and most of the activities will interact with the users. And so there will be a main activity, an activity that responds to an event where the application is actually opened by the user. Most of the things in Android world will be asynchronous, which means that a lot of the functionality that's executed by the applications will be triggered by some sort of events that happens and it's within the operating systems, like receiving SMS or boot completed or so on. And there are these communicating packages which are called intent. And intent is a way to communicate that one part of the system or an application wants to do something with the whole system or with one specific application that you want to target. So, you know, when the boot completed, this broadcast is sent to all of the system, and then there are components that are called receivers. Receivers specifically state that they are interested in certain intents. So they want to filter certain messages from the system, such as boot complete or SMS received, that you will then do something with that package of the information. So this is one of the typical ways how some malicious applications are making sure that they start up when the phone has been booted up. And finally, the last bit of the last significant that are important for the reversing of files is called the service. And service is any piece of code that runs in the background, and it doesn't necessarily have any kind of user interface. So now we have at least some basic understanding of what, like Android, how the operating system looks like, which objects are there which we should look at, and also how do we start. We usually start with looking at the Android manifest. And so I mentioned at the beginning that there are really some good tools, and probably the best tool to start with is Android SDK, Software Development Kit, and also Android Studio, which is of course the integrated development environment that's kind of like a clone of IntelliJ. And here you could see why is it good. Like if you're very much into command line, then you're not going to use it. But this is the simplest way how you can start both building or developing Android applications, but also analyzing and creating your own environment for malware analysis. And why I'm saying that here in the top right corner, you may or may not be able to see that, but there are some devices here. And so Android Studio is integrated, and you can actually install various versions of SDK through it, and then it also allows us to create virtual devices, and those virtual devices can then be used to push applications, debug applications, and then in the bottom window, the very useful functionality is called logcat, which is basically just concatenating many of the log messages that are coming for many applications. And as you debug, you can see the messages coming from your own app, but also from some other applications within the operating system. So immediately we have some environment that it doesn't really take too long. It takes a little bit more of the disk space, but we have something that we can work with relatively easily. If we only want to use the command line interface, then as a part of the SDK, there is an application called Emulator, which emulates, which is based on QEMU, and it emulates creates the Android virtual device and also can launch Android virtual device. And here we see an example of how we can, what sort of call we can do to launch an emulator. So we call an emulator. There's also an option to run TCP dump on all the network data and create pickup files. We will pipe the logcat output into a file so we can go back when we analyze something, and then eventually just call the name of the Android virtual device. So it's relatively easy to do. In terms of the communications with the virtual device, or not just the virtual device, any device you have connected, so you can connect a real device over a USB and enable developer mode, so you can kind of run debugging for that particular device, which is for the virtual device enabled by default. The main way to communicate is through something that's called Android Debugging Bridge, ADB. ADB has many functionality. You can start ADB as a root on the virtual device side and then launch a shell, and then as a shell you have like normal, more or less Linux commands. You can install APK files, you can push, and download the files, you can upload and download the files through ADB, and you can also get all the logcat messages. So it's kind of like a Swiss knife for some of the debugging tasks for command line. And within ADB, there are many different commands. One of them that's useful and that I kind of use relatively often is for application manager, AM, which allows you to start any application and any activity within that application. Package manager also allows you to list which applications are installed at that particular time. One of the main tools you use for Android malware and in general Android decompilation and reversing will be a decompiler. At the time when I was doing the work, it was called, or it was JDGUI, which still exists. But in the meantime, JEDEX is the most useful one. For many people, it works for like probably more than 90% of all samples that can be decompiled with JEDEX. It has some deobfuscator by default, so here we have to be a little bit careful. If we deobfuscate some of the names and we look at the manifest file and we search for a particular class, we may not be able to find it, so we have to roll back the deobfuscation to try to find some files, but overall it works really well. If that doesn't work, then the bytecode viewer has several decompilers included, and so you can try several of them if one of them doesn't work. And eventually, if that doesn't work, then APK tool creates a dump of the, let's say, source code, or actually Dalvik bytecode that's called Smali, which I think in Icelandic means the assembler Smali, and there is also a Bug Smali that's a tool that disassembles the thing, so it's a disassembler. So here's just like how the JEDEX GUI look. JEDEX has both graphical user interface and command line interface, but generally when you decompile a file, and this is the same Metasploit payload that I looked at the beginning, is you get pretty reasonable and pretty readable Java code, and so you need some just basic understanding of coding in Java. You will be able to understand, unless it's like super obfuscated, and that's a completely different thing and outside of the scope of a quick presentation like this. So I already mentioned APK tool that kind of allows you to decompile the manifest file and create those Smali opcodes. APK tool allows you to disassemble and then build back the APK file. So sometimes when you want to circumvent some functionality, like if there's some kind of anti-debugging functionality, you may be able to modify the actual Smali source code and then put together the APK file again, sign it, re-sign it, and then you'll be able to work without kind of anti-debugging detection, for example. Every application also has debuggable attribute, and so if that attribute is set to true, you'll be able to debug that application using JDB, Java debugger, and maybe even like Android Studio that underneath uses JDB. There are some tools that are useful for triage. One of them is called Quark Engine. It's kind of like a set of Python script that kind of disassembles or kind of takes apart the APK file, looks into classes.dex, finds suspicious functionality, gives it a priority, and then basically you can drill down. You see, okay, it's using SMS, it sends suspicious data, it uses, I don't know, base64 decoding. So you can then quickly see some of the points in the applications that are useful. It's similar with the APK ID and Droid is whatever. And then finally is the Frida instrumentation toolkit, and that's good for kind of almost anything, but it's kind of a dynamic side of the analysis. One of the very neat tools is a module for VS Code called APK Lab that allows you to do many of these things without having to type everything in command line interface. It allows you to open the code, run Quark engine on the file, so you can do several tasks and you kind of click and choose, and suddenly you have both Smiley code and Java because JDEX is run in the background and everything is used in the VS Code. It also allows you to remove certificate pinning functionality through some scripts within the APK Lab, and also rebuild the file again. So it's kind of like a very, very useful set of tools for analysis. So in terms of the static code overview, what are we looking for? What are we trying to find? It will be, some function name which are typical for when applications start up. We have onCreate. You instantiate or you inherit from the application class. You create your own application class. You override onCreate function, and this is often the entry point in the file, but there will be some other ones, like also some receivers. So there is a set of callbacks that are called by the system and which we need to implement in our applications, and that's what the malicious code is also implementing, and that's what we're trying to look for. And then we look for some strings in the file, if there's an HTTP, for some URL or some indicator of compromises. Is there a check for super user functionality? Is there a check for Genymotion or QEMU? So some of the malware is trying to see if they are analyzed in some virtual environment. And so those will be the usual suspects, which we'll try to see when we kind of doing our own initial triage. So now we can go to Frida. It's Frida probably exists maybe for 10 years, a little bit less than 10 years, and it's a very powerful tool for dynamic binary instrumentation. It's similar to PIN or Dynamo Rio, which has a much longer development cycle. With Frida, it's you use JavaScript, which for me was like a big no-no. I really don't like JavaScript. To instrument kind of binary instructions, to instrument assembler code, to instrument blocks and instrument the functions. So on the one hand, we have assembler and machine code, on the other hand, JavaScript. So like how does it all work together? Somehow it's like it's magic, but it works. And Frida is de facto standard for dynamic analysis or binary instrumentation for Android, but also on iOS. And so you have several components in Frida. It has a client. This is the app you are creating, your own scripts. And then there's a core functionality, which is on the server side. And then that core functionality is built in like a Frida server, which you have to install and run on the target system, like a virtual device if you're using virtual device. The system doesn't have to be rooted. So there is something called Frida gadget, which is a shared object that then gets loaded with the APK file within the process space, and so you can use it that way. And that's not the only way, the principal way how you use Frida on iOS. So here is like a very high-level overview. On the left, we have our own tools. So our own JavaScripts, which we create to instrument certain functionality to override something. And then there is a communication bus and that communicates with the server side. So both client and the server can be on the same machine, and so if you do a Windows instrumentation, you will typically maybe work it on the same machine, but with Android you will have usually your client on your host, and then within the virtual device you will have a Frida server for this particular version of the operating system and for the particular process architecture. So how do we run Frida? At the beginning it's a bit unnerving, I have to say. You know, what do? I know that it can do all these things, but how do you then do that? And luckily it's very well documented, and there's a very strong community around it. So the principal way of running Frida is simply by first of all, you install Frida by running pip install Frida tools. It could not be simpler than that. And then you have a Frida command line tool, which you can run Frida. -U is for USB. -O is where do you want your log to go to. So everything that's written to the standard output can go into the log file. Then you go -L, which JavaScript file you want to load within the process space of your application, and then which applications do you want to run and instrument. So there's not much more than that. So you only need few bits and bobs, and perhaps you will use no pause function, so the application runs immediately, and your scripts will then run after that. Frida together with Frida, when you install it, it's not just Frida itself, but also a number of other Frida command line tools. So Frida Trace is also like a great place to start. It allows you to instrument both native API calls or functions, but also on Android Java functions. So for example, if I'm interested in unpacking files, I know that a malware may load some file drop some file to the disk, load it into memory, then delete the file from the disk. So if I look at the before and the end of the execution, I don't see anything on the disk. But I can use Frida Trace to instrument all the open functions in the operating system, and then I'll see which files were actually open. I can do the instrumentation of write and tracing of unlink, for example, deleting. So I can see that the file is trying to open, try to write something, and then unlink something. And then I know, okay, I need to do something furthermore. So it's a very good triaging tool for the first level. And then there is also Frida PS that lists all the applications that are installed on the system, all the APK files, and so on. So here's how I just run a Frida Trace for one function. One function on the application that's called main activity, which is this Metasploit thing. And I knew that the Metasploit is running a parse configuration function. And so by default, Frida Trace is kind of like you give it a pattern, and then it goes into the application space, and it tries to find all the functions which match certain pattern, and then it instruments those functions. So it found one function which I already knew before, parse config, and then it logs both entry parameters and the return call. So you get log both entry and arguments to the functions and return functions. And the way it does that is it creates an underscored handlers folder where you run the tool, and in that handler folder there will be a number of JavaScript files. And you can see here that in a JavaScript file you will have two functions, one on enter and the second one on leave. So this is what Frida Trace does. So it creates JavaScript and it uses internally Frida. It kind of creates this framework of boilerplate code. And you can see here how the config function, parameconfig, is called. These are the arguments, and it logs those arguments. So in the next step you can actually modify this JavaScript code. And one of the best ways to modify the code is, to write a script for yourself. And this will be like a script structure for Android for Java Bridge. So there is a Java Bridge which you launch by calling java.perform API, JavaScript API within JavaScript, and then you give it a function which you want to run. So the function will be run. In this case, the second code is Java use. Java use tells me I want to take one class from the Android side of the world, and I want to move that class to JavaScript side of the world. So now my variable called Z represents the Java class on the Android side called com.metasploit_stage.config parser. And so the next thing is I want to do, I know that I'm interested in the parse config function. So what I do next thing is like I try to do z parse config function. I overload that function with the byte array parameter and I implement it as some completely different function. So when I load that script, instead of the parse config of the Metasploit application, I will have my own parse config, and here I can do whatever I want to do. I take the arguments, I modify the arguments, I modify the return value of the function, and I return anything I like. So you can see how powerful this can be. Like even if anybody's doing CTFs on Android, they will be probably already, they probably already know about Frida, but it gives you some hackish way how you can circumvent some functionality, things such as detecting of root or so on. Frida also has like a command line interpreter. If you just launch it like Frida something, without the script name, it will go into the process space of the application. And then you can run all these commands from a command line. One very useful functionality, which I've at least found out, is called java.choose. So this allows you to go into the memory of that application, and it will look for all the instances of a particular class. So here I was looking for the configuration instance. So I looked at com.metasploit stage. I can't read anymore. But anyway, I looked at the object, and I took a certain, so when that object is matched, every time we find it in memory, we send that instance to my own function, to our own function, and then we can work on that instance. So instance is the instance of the object class we are looking for. We are going for the URL field, and we're going for the value field. So here I'm looking at the Metasploit configuration URL for command and control server. And we see two lines here, identical lines, because I run that main activity twice. And then the more you run it, the more objects will be instantiated in memory. And we see that we managed to enumerate all of the configuration objects, and we extracted those URLs for Metasploit. So it's super, super useful. So first thing, like I think I already mentioned, we are looking at the manifest, we look at some suspicious permission, we are looking at the main label to see which activity will start, and does it use accessibility API, and so on. The next thing what we want to do with analysis is to look for the command and control functionality. We will try to find the functions which instantiate that functionality, to see what other pieces of infrastructure we can get to. We find all the command and control routines. We now try to do some man-in-the-middle attacks to log all the packets in a burp or some man-in-the-middle proxy. So we can do it basically two ways in terms of intercepting. One is we can find which actual function is used for command and control functionality, and then we use Frida to instrument it, so we can log return values or entry values or change its own functionality. Or we do SSL man in the middle, and in that case we often need to make sure that the certificate pinning is not implemented in the application, and if it is, in that case, probably the best way to do it is to go to Frida Code Share, and in Frida Code Share there are scripts like several scripts that basically allows you to bypass certificate pinning in Android applications. So that's codeshare.frida.re. It's not super well organized, but you will find a lot of good scripts that are used for common functionality when you do some reversing. APK Lab is the other thing that can allow you to do that, only with a graphical user interface. So we'll go into a couple of tricks, and I think I already more or less mentioned one. There are many applications which can be packed, which means you have your basic classes.dex, but sometimes somewhere within the APK file, or maybe even on the internet, you will have the next stage in the functionality of the application, of the APK, of the malware functionality, and that will only be loaded later. So what we try to find out is if there's something in the manifest file that's declared and we can't find it in Smalley code or we can't find it in Java code, then there's a suspicion that this file could be packed. So that's only loaded later. And so I already mentioned that you can create a triage script which will log all the opens in the operating system by that particular file, and then it gives you, tries to open this file, tries to open that file, and then you will get the file names which are probably quite suspicious to be the actual next stage. So if the payload was not there, I think I already mentioned that, then we can try to instrument the unlink or delete function. So we try to delete file, we just return the success, but in fact we don't delete the file on the disk and then in the memory, and so once the malware finishes the execution, we just go add ADB pool and we pull that next stage, and then we can then analyze it in normal decompiler. So that kind of how in theory works. In some cases, they'll be only loaded from the network to the memory, but in that case, we can instrument in-memory DEX class loader and just dump the DEX class. There's also a FRIDA tool called FRIDA DEX dump that goes into the memory of the system and tries to dump all the DEX files which are there. So here's the example with here we are trying to find the native function by export name in any library that's called unlink. And so we are trying to hook unlink, and there's this for native functionality, the main way you instrument the code is through the module called the interceptor. The interceptor allows you to instrument native, while Java allows you to instrument Java side of the APK. And so here we are trying to find, okay, if the certain file name is tried to be deleted, in that case we just say, okay, we didn't delete it, and we return some specific, we change the argument in this case and run the original unlink, I guess, and it won't delete anything. So that's a simple trick. The next thing we'll try to do is to circumvent those emulator checks. So here we see that at the beginning in the first line, there are some strings like proc.tty drivers, proc.tty CPU info, which will be called to check whether the QEMU drivers are loaded. So, and in both of those functions are Boolean functions, and so we can, as you can imagine, use FRIDA to intercept those functions and simply return false in this case, that we didn't find any emulating environment. Another common check is for file names and programs which are associated with the fact that the phone has been rooted. And here, you know, we can see some code, and that code goes, if I see certain files existing, the other way to do it, one way is to instrument the FRIDA, and the second way is to actually change the Smalley code. So instead, we go into Smalley, into file system, we try to find all the Smalley files that contain certain strings, which are these strings that are checked, emulator checks. And then instead of if not equals 0, we change to if equals 0, and then we recompile the file. So we are now checking, first check is whether certain file names exist. And so that we convert that if not those files exist. So that's like a simple way of how you can patch the application. Like I said, you need to recompile the file, so you put together all the Smalley, you create the APK file, you have to zip align it with the tool, and then eventually you sign it. It really doesn't matter with which distinguished name you're signing it. Where we are. Oops. Okay. So this is a very similar way of doing the emulator checks. we can either hook open function, and if file doesn't exist, it will already default to file, and or override the implementation method and simply return something that we like to return. The trick is that sometimes if we want to instrument something, it's not yet in the memory. So we go back to our open instrumentation of open function call for the operating system, and then we only have to see which file will be the main, the next stage of the malware, and when we find it, then we go back into the Java code to see when that file is loaded. And only when that file is loaded, only then we can instrument the Java function, when the classes are already loaded in memory. So here what we're trying to do is we do our own open, we instrument natively open function, and when we open a particular file name, only then we know we can do java.use, and then we instrument emulator checking function, and then only then. Otherwise, before that, we will get an error. So Frida is a lot of trial and error. And so this kind of brings us to the end of this super quick and super compressed course on some of the malware or reversing on Android. So things we have to keep in mind: Android is very much asynchronous. There are a lot of callbacks you need to check, you need to be aware of. It's very well defined, so it's well documented. The different versions of different level of SDK will result in slightly different behavior as well, so there's a little bit of a trial and error. Manifest is the first thing that you look for, and then you look at the permissions which are declared. So SMS read or accessibility could be a banking Trojan or some phishing thing or some stealer. Audio recording, geolocation will point towards some remote access Trojan. Boot completed means the receiver means I want to run this functionality when the system is booted, and so on. So with that, there are a couple of slides which I will share, I think, with Jelena and Milos, and then perhaps we have some time for question and answer. So that's more or less all. Thank you. Any questions?
Okay, you mentioned several times that a lot of Android malware is exploiting accessibility services. So can you elaborate on that? In which way?
Okay, so accessibility services allows you to, let's say, read the content of other applications. So you can register your application which uses accessibility service to get a notification when certain application is the first one on the. So if you have, let's say, a banking application, and you know that the package name of the banking application, your app will get the notification when banking application is launched, and so you can either overlay the code of the application to get username and password or whatever, to steal something. You can read the content, you can modify it, you can basically make the clicks for the user, like if you automate something, and the accessibility functions allow you to do all that. So if you try to, for example, one other example is you go to configuration and you try to remove some application. You can get that information as well, and then you can send back click or home click. So you never are able to, using the user interface, remove that potentially suspicious application. So there are like weird things can start happening on the phone. And so there are a lot of possibilities to steal the data, to modify the behavior of some apps, or overlay some user interfaces with the elements where the user will not even know that they are not part of the actual application.
And in order for that method to work, does user need to turn on some accessibility feature, or it works by default?
When the accessibility features are required, then the user will be asked for that particular permission. So it's kind of a runtime thing.
Thanks.
You mentioned on one of the slides that anti-instrumentation features are rare. What kind of features have you seen in the wild?
A good question. Personally, I don't remember anybody really on the APK side targeted Frida as such. Whether it's possible, it's definitely possible to detect it. If you have a Frida gadget, for example, is the shared object that you pack together with an Android or an iOS file, and by default it's called frida-gadget.so or something like that. So you can guess that name, or you can basically maybe look in the memory or the loaded modules where there's already Frida gadget, or you can try to find out where the Frida server process is running on the system. So if there is some more, let's say, advanced app, they may be able to check. I don't remember actually seeing it, and that's why I guess we said it's rare.
Okay, I would imagine that it was like similar to anti-debugging or anti-VM stuff.
Similar, like simple tricks work if you use default option. That's the thing. But if you try to disguise Frida in some other ways, you know, it's less likely it will be detected. But I guess people are not that much aware, like on the malware development side, that you can do all these sort of things.
Sadly, that is all the time we have. Everyone, please, an applause for Vanja.
Thank you.